So let's explain what's happening here and also try to find out how this raft and water system is equivalent to a spring mass system. So let's draw a crude diagram of this water and raft system. So we have a raft, which is this um, black wide line, and then there's a man standing or sitting on top of it. So what's happening here is the force of the man's weight causes the raft to sink because the gravity is acting downward. So whatever force the man is putting on the raft, that's making the raft to sink. And we know that there's a buoyant force for water, so that means there will be buoyant force which will prevent the raft from sinking. So this black arrow is basically the force due to man acting on the raft, which is trying to sink the raft, and then this blue arrow is the buoyant force of the water trying to um, make the raft afloat. So the extra buoyant force due to the man putting so the extra buoyant force is arising due to the man putting the extra force on the raft, and this is kind of a restoring force because it's in the opposite direction of the force put on the raft by the man. And this is analogous to a spring mass system. So let's say we have a spring and then we have a mass, and that's an equilibrium. So if we put extra force, it will try to now go down, and then since it's a spring, so the spring will try to restore its equilibrium position, so it will try to pull the block. So that's how it's analogous to a spring mass system. So when the man steps off the raft, the restoring force try to push the raft upward because this force is not present anymore. So that's why the buoyant force that's present here, it will try to push the raft um, upward, and that way the raft water system will act like a spring. So with the spring constant, we can calculate that as force external that's being exerted by the man on the raft divided by x, that's the displacement. So using the given information, we know that force external will be m times g. So m is the mass of the man, which is 68 kg, times gravity, which is 9.8 meter per second squared, and we divide that by the displacement, which is 3.5 times 10 to the power negative 2 meter. So that gives us the spring constant as 1.904 times 10 to the power 4 Newton per meter. So now we know the spring constant. So in part A, we have to find the frequency. So the frequency of vibration is determined by the spring constant and the mass of the raft by this following equation. So we have frequency of vibration that's equal to 1 over 2 pi square root of k by m. So that's 1 over 2 pi square root of 1.904 times 10 to the power 4 Newton per meter divided by 320 kg, which is equal to 1.228 hertz. And if we approximate to just 2 sig figs, it's just 1.2 hertz. Then for part B, we have to find out the total energy of the oscillation, and here we're ignoring the damping. So as we explained in the text as we explained before, excuse me, for a vertical spring, the gravitational potential energy can be ignored if the displacement is measured from the oscillator's equilibrium position. So let me draw that spring mass system one more time. So if this is the mass and this is the spring, so if we take this as our origin, so that means there is no gravitational potential energy at this equilibrium position. So we can ignore that. And then the total energy will just be uh, elastic potential energy. So the total energy is half of k a squared. And of course, since it's in equilibrium, there's no velocity. So all we have is the potential, elastic potential energy. So now we can use the given information. We have spring constant as 1.904 times 10 to the power 4 Newton per meter times a squared, which is 3.5 times 10 to the power negative 2 meter squared. And um, we got that from the problem that that's the displacement basically. So this is equal to 11.66 joules. Thanks for watching. I'll see you next